Good afternoon, ladies and gentlemen. I am Manas Samal, Faculty Astronomy Astrophysics Division, and I'll be coordinating this ceremony today. So first and foremost, I kindly request you to take your seat and please keep your mobile phone on silent mode. Friends, it gives me great pleasure to warmly welcome you to all second Ravipati Raghavarao Memorial Lecture. This memorial lecture has been instituted to honor the legacy of Professor Ravipati Raghavarao, an eminent scientist and a distinguished member of PRL. This memorial lecture to formally begin the today's ceremony and welcome all the dignitaries. It is my privilege to invite Professor Bharadwaj, Director PRL. Please come to the stage and give your opening remarks. Professor Bharadwaj, please.
Namaskar, Suprahan. Very warm welcome to all for the second Professor Ravipati Raghavarao Memorial Lecture. We instituted this lecture 2 years back based on the request from the family of Professor Rao to have this endowment funds available to PRL to have some kind of ceremonial function in the honor of Professor Rao. And we are delighted to have Shri Shanti Sagar with us today, who is the son of Professor Raghavarao, and also two of his friends who are also with us today attending this function. So we started this last year with after the approval from the council that we will hold this kind of memorial lectures as a part of the award ceremony. And alternatively, it will be given to an eminent junior scientist and a senior scientist. So last year we had hosted the junior scientist memorial lecture. And this year we have Professor Devendra Ojha, Professor of Department of Astronomy Astrophysics in Tata Institute of Fundamental Research in Mumbai, as an eminent speaker for the second Ravipati Raghavarao Memorial Lecture. So welcome, Professor Devendra Ojha. This memorial lecture is awarded in the areas of science being conducted in PRL. And we know very well that we cover a very wide domain of research in PRL, starting from astronomy, astrophysics, space and science, solar physics, geoscience, planetary science, atomic molecular optical physics, and theoretical physics. So it's a bit difficult to, choose a person with so many different applications coming from different backgrounds of research being conducted in PRL. And we thank the selection committee for doing their best in selecting the best. And that's how we have Professor Devendra Ojha today with us today. This memorial lecture is actually the third. I was just talking to Dean on this issue, that in recent past we have started couple of other memorial lectures, starting with the Dr. Vibha Chaudhary Memorial Lecture, which is started during the COVID period in 2020, 21, 22. And then we also started Dr. Arvind Bhatnagar Memorial Lecture to honor Dr. Arvind Bhatnagar, who founded the Udaipur Solar Observatory, whose Golden Jubilee we celebrated very recently last week when we hosted an international conference in Udaipur, because that is also a very unique occasion that USO has completed 50 years of its existence, whereas PRL has completed 70 years of its existence. So very soon we are moving towards 80 years of existence of PRL. So we'll be very delighted to hear the talk of Professor Ojha on the title Observational Astronomy of Star Formation in the Milky Way and Infrared Instrumentation. My colleagues will be describing more details about Professor Ojha, but I know Professor Ojha for close to 2.5 decades, and more in interacting with him as a member of the board of TIFR balloon facility, where I have been interacting with him for almost like one solar cycle at least now. And he's an expert in infrared instrumentation, and will be giving you glimpses of how infrared instrumentation is used to understand the star formation and its evolution. So welcome everyone to this second memorial lecture in the honor of Professor R. Raghavarao. And I warmly wish that we will have a wonderful lecture from Professor Ojha. Thank you. Thank you very much.
Thank you very much, sir, for your inspiring opening remarks. Now I would like to invite Professor Pallam Dean PRL, to inform the audience about Professor Raghavarao and on whose name this memorial lecture is instituted. Professor Pallam, please.
A very good afternoon. It's indeed a pleasure for me to recount one of my great grandparent in terms of academics. He was Professor R. Raghavarao, was the guide of my guide, Professor R. Sridharan. So it's a great honor for me to talk about Professor Raghavarao. Professor Ravipati Raghavarao is fondly known as RRR. Okay, so he was more famous before the movie RRR. So he is all known as RRR. Was an illustrious faculty member of PRL and served in PRL from 1966 to 1989. Professor Raghavarao was one of the pioneers in the field of astronomy, covering all the theoretical and experimental aspects of upper atmospheric investigations, whether it's ground-based, radio-based, optical proving measurements, or satellite-based experiments like the topside sounders or rocket-based experiments like vapor releases and in situ measurements. He obtained his bachelor's and master's and the doctor in science degree in 1960 from Andhra University, Visakhapatnam, with Professor B. Ramchandra Rao as his supervisor in the field of ionosphere. As a young and aspiring postdoctoral fellow, ready to take up challenges, he went on for a couple of years to the National Research Council, NRC, Ottawa in Canada, to work on a project related to the 9.3 centimeter radio survey of galactic plane, making significant contributions. He soon returned to the field of ionospheric physics, the topic that he loved most throughout his life, and worked from 65 to 66, another couple of years, at the Department of Geophysical Sciences in the University of Illinois in Chicago, USA. He returned to India in 66, and soon he was invited to join PRL as a faculty by Professor Vikram Sarabhai. He was one of the scientists. He was one of the scientists who established the topside ionospheric sounding station in PRL during the late 1960s. Using this facility, he and his students soon discovered the characteristics of another feature called the topside ledge in the ionosphere. He and his colleagues conducted several successful campaigns of upper atmospheric wind measurements from Thumba Equatorial Rocket Launch Station, also known as TERLS, by using photographic tracking and triangulation of rocket-based vapor clouds. Later on, this was followed by the development of optical techniques for daytime optical measurements. He also initiated and sustained electric field measurements in the ionosphere by vapor cloud release experiments. He gave a new dimension to an impetus to the optical aeronomy program in PRL that led to the innovations of the day-glow measurement techniques and to build state-of-the-art high-resolution imaging scanning spectrometers. Many of the experimental confirmations of his early theoretical predictions have come out to be true after several decades. So that was what his insight and foresight was on various aspects of this field. All through his research life, he always developed ideas first and then went about looking into data or proposing experiments to prove or disprove those theories. He never believed in serendipity, nor did he want to thrive on it. He was a selfless person with a far-sighted vision, a passion for science, and indomitable spirit of pursuance. He clearly recognized talent wherever he found one and gave wholehearted encouragement for the growth of such talent. He had played a major role through his advisory capacity in shaping the space science program in the country. He was a true beacon of the aeronomy science community, much sought after by the fellow generations. Most of all, he was a very fine human being. He was an elected fellow of the Indian National Science Academy and a recipient of the Kalapati Ramanathan Medal of INSA in 1996. He was interested in all the areas of sciences being pursued in PRL and was a regular attendee to all the seminars and colloquia held in PRL, which is one of the most unique aspect of Professor Raghavarao. And he actively interacted with all the faculty of PRL, cutting across the research domains. So it's kind of almost a kind of interdisciplinary figure and a constant presence in any of the seminars and colloquia that happen. So this is just to say, a very brief account of what the person Professor R. Raghavarao was and the kind of interest he took in various aspects. There are many more things to talk about him, but at this point of time, I just wanted to submit to you this brief introduction about Professor Raghavarao. And I thank you all for your patient hearing. Thank you.
Thank you very much, sir, for your insightful deliberation on illustrating career of Professor Raghavarao. Friends, we are especially privileged to have with us today Sri R. Shanti Sagarji, son of Professor Raghavarao, in this auditorium. With great honor, I invite Sri Shanti Sagarji to kindly come on the dais and share few words about Professor Raghavarao's vision, life, and your memories. Professor Shanti Sagarji.
So good afternoon, everybody. So first of all, I'd like to thank everybody for just sparing the time, coming down, and attending the memorial lecture. And I'm sure my sister, mother, they'll all be happy about seeing all the audience here. And just a few thoughts, memories, from say our family life and the personality of Dr. Raghavarao. About the memorial lecture, after my father passed away, say it's now 13 years, 13 years, we decided we'll institute this memorial lecture in his memory to kind of, just, sustain some of the values that he professed during his work life, and which he held, very dearly to his heart. And of course, the place. When we discussed within the family, I said, it has to be PRL. So everybody decided, this whole place, this landscape, this area, this is where he kind of expressed his dreams, his passion for work. So we thought this is the right place for, the memorial lecture. So it's almost a no-brainer that PRL should be the venue. Just a few thoughts about my father, which some of you may know, some of you may not. He was born in, this thing is into an agricultural family, very large family. In those days, I understand, families used to be very large. I mean, my dad's family was about 13 kids. So the idea being that at least, child mortality being high, some would survive. So I think finally 9 survived out of 13. And few interesting things are like my grandfather, paternal grandfather, was very much against education. I mean, he used to think, this education is just, just a waste of time. The kid should get into the fields and start working and, growing crops, bringing money. So even at that age, my dad resisted his dad's, negative attitude and insisted on going to school. He used to, I used to keep hearing this. He used to probably walk for miles, just to attend the nearest school. He completed his schooling. So it shows just his love for education and just to come out of the feudal agricultural mode of life. And being the eldest in the family, he kind of had to set an example, which he did. And he helped his brothers. He made sure one brother became a doctor, one brother became an engineer, another became an agricultural scientist. So this is just one of the values, like his love for education and, to go for a different lifestyle, breaking away from the field, the farm, and which he was born into. So Few other things I kind of remember was after his whole PhD, like Dr. Pallam Raju shared, he finished his PhD, and in fact, after he went abroad, he came back, and he was not having a permanent position in the university. He was having a kind of a temporary post. So he was not very secure. So interestingly, my mother had, yeah, now it's nice. It's good to touch on my mother's topic, because his this love for education, what I was speaking about, it went to the extent that he chose his life partner, my mother, because she was highly educated. She was a PhD in statistics, and in those days, what I was told was they used to just marry within the district. They never used to even look very far for a bride. Even, I mean, you forget about love marriages and all, it was all arranged marriage. So he married from a district which was quite far away. And so that was something unusual. And then another um interesting thing was, uh, a dowry system was so common, so rampant. And my grandfather was very traditional. He said, you went for education, you better get some good dowry to compensate for all that. So you made me spend on your education, and first place, you shouldn't have gone for it. And then my dad, just married without a dowry. He said, I won't take a dowry. Then my grandfather, this is all like, the family talk. So literally my grandfather issued a kind of, you can call it a fatwa, that my mother should not visit my father's village. Period. She should not visit. They're not allowed to come. Didn't get in dowry, that's it. And she didn't come. She never visited my dad's village for years and years and years. So just, I mean, his passion, like he was, because of my mother's education level, so dowry was out of question. So these are, some of the interesting minor details. Even maybe Dr. Pallamraju may not be aware. And then just coming back to his postdoc, he did his postdoc, came back. Like I was saying, my mother she was having a permanent job. She was very secure. My dad was not so secure. And what I heard in the family say talks was, for one seminar, my dad went to present a paper. And Dr. Vikram Sarabhai was there in the seminar. He heard him out. And he just came up to my father and said, see, why don't you come down, to Ahmedabad to join this institute? That was a period, I think, when PRL was in a formative stage. So said, you just join the initial core team, and it was a good opportunity for my father. So I'm just like throwing light on how Dr. Raghavarao happened to come to PRL. So it was looking good. And then there was a problem because my mother had to make a sacrifice. She was in a very secure position in another university, and she said, see, it's not easy to get this kind of post. And Dr. Vikram Sarabhai was told that, see, my wife is having this post, and she can't come to Ahmedabad. So that's the problem. So Dr. Vikram Sarabhai, he said, there's no problem. See, you here, in this incident, you get an insight into Dr. Vikram Sarabhai's, skills at attracting skills, to where he wants them to come. He was, I mean, he was not just a genius in physics. He was extremely talented in many things. He could get the people he wanted somehow or the other. So he made a proposal to my father. He said, okay, I will ensure your wife will get, my family has companies in Ahmedabad. They are a business family. We have, so your wife is from a mathematics background. So I'll fit her into some accounts department somewhere. I still remember he got her a job in Calico Mills. Some of you may have heard of Calico Mills. One of, in those days, Sarabhai was a big group here. And she actually went, joined there. So that's how that problem was overcome. That's how Dr. Raghavarao came, joined PRL. And my mother used to go work there in some finance department in Calico Mills. Well, eventually she had language issues working there. So I think later on, I'm not too sure about that detail, but she joined PRL and she was responsible for starting the computer science department here. So they're probably one of the few couples who actually worked. I mean, you can say my father and mother were married to each other, and both of them were married to PRL. There's a way of putting that. Then so I just kind of made, because I was not expecting to be asked to speak. Then Dr. Palamraju today morning said, he told me you just say a few words. So I just made a few notings. And the other thing is, why have a memorial lecture? You can just have an award in his name, give it out, give a certificate, give a medal, give some cash. I mean, just be done with it. It's over. No, it's important to have a lecture because Dr. Raghavarao had, I mean, this is just my personal view. He had this very strong conviction that a scientist should be able to, communicate his ideas, to have a, threadbare discussion, and that's how really science evolves. So that's the reason for the format of having a lecture, simply to ensure scientists develop communication skills. And we all know in every field, politics, business, everywhere, we need communication skills. And equally so in science and administration and business and everywhere. So that's the thing about the lecture format. So one more thing I can recall, in younger days, I used to go, maybe me and my sister used to go, we would watch a movie and come back. So when my father used to say, you just tell me the movie story. I said, like, I do want to hear the story. I gone, seen the movie, got entertained, came back. So no, you tell me the whole story. Then I used to tell him, this is the story, this is the plot, this is what happened, this is the beginning, this is the middle, this is the end. And later on, I realized this is his way of, getting you to express yourself, to develop that power of expression. This was his whole style. And I'm sure he did this not just with me, but with many of his, other students and colleagues, people with whom he used to work with. And see, Ben, my life here in PRL, it's not just Dr. Raghavarao. You know, this when we talk of you just compare PRL with a kind of something like a constellation, galaxy, like what Dr. Ojha is going to talk about. So you have so many stars. I can't forget the names. There's so many professors, so many. I mean, I know those names as well as, say, any of my friends, like, you know, whether let it be Dr. Chitnis, Dr. Kulkarni, say Dr. Pandya, Dr. I mean, it's a long, long list. You know, this way, in case I forget Dr. Bhavsar, Dr. Kau, Dr. UR Rao, Dr. Agarwal, Dr. Sastri. There's so many of them. So all these, kind of Dr. Sarabhai, who is, you can say, who's brought all these stars together and made this constellation of scientists, here and built, this big kind of institution. There, there were just so many names and stars behind what you see today. And then about the award, the award, it's to recognize and reward outstanding contributions. Like Dr. Bharadwaj was saying, 1 year for young and the younger scientists, and then following year, the senior scientists. And it gives, I mean, there's a lot of silent hard work going on. This way you recognize that hard work, you reward it, and it encourages more and more of the same. Last year I was here and there was a young scientist, Dr. Agarwala. So it was very useful. And even for me, I'm not a physics person, but I still remember all the talk about neutrinos, and so it stays. A lecture format, it stays in the mind, because currently everybody, younger generation, even my generation, we get used to mostly seeing videos, visuals, and you just see it and you forget it after some time. But you hear something, a lecture, and then it stays with you longer, I feel. And so these are just few of the personal things I thought relevant to share with the audience. And before I conclude, I'd like to just express my thanks to Dr. Pallam Raju, Dr. Anil Bharadwaj for all their efforts in organizing in the selection of the winners. And that's something definitely praiseworthy. And also all the committee members who take time out for evaluating the applications and deciding the winner. What I'm told is there are almost 20 to 30 applications from all around the country which come in to get this award. So that's encouraging, and hopefully the numbers will go up with each year. And we miss here today Dr. Sridharan, my sister, Dr. Shobha. Wish they were here. It would have been better. And my mother. And finally, congrats to the winner, Dr. Ojha, on winning the award. And wish you all the best for a successful career and more achievements. Thanks, everyone.
Thank you, Santi Sagarji, for your heartfelt words and sharing such meaningful insights of Professor Raghavarao. Your reflections have truly enriched this occasion and help us to better appreciate the enduring life of Professor Raghavarao. Thank you, sir, for coming and joining us. Ladies and gentlemen, we now come to the very special moment of this evening, the felicitation of second Raghavarao Memorial Lecture Award to Professor Devendra Ojha, Senior Professor, Tata Institute of Fundamental Research. As a part of this honor, Professor Ojha will be presented with a silver plaque and a citation. May I now request Professor Devendra Ojha to kindly come onto the stage for receiving the award. To do the honors, I invite Professor Bharadwaj, Director PRL, Professor Pallam Raju, Dean PRL, Sri Santi Sagarji, to kindly come on the stage. I also request Professor Sachindra Naik to come on the dais and read the citations. Professor Naik.
Thank you, Manas. So it is my honor and great pleasure to read the citation for Professor Rabipati Raghavarao Memorial Lecture in Eminent Senior Scientist category. Professor Devendra Ojha, Tata Institute of Fundamental Research, Mumbai, has been selected to deliver the second Professor Rabipati Raghavarao Memorial Lecture for the year 2025-26 in recognition of his significant contribution in galactic astrophysics and astronomical instrumentation. This citation has been signed by Professor Anil Bharadwaj, Director PRL, on 18th February 2026.
Thank you, Professor Naik. Now I request Professor Bharadwaj, Professor Raju, and Professor Santi Sagarji to please present the award. Now I request Professor Ojha to kindly take the seat of the dais. So, friends, it is really our honor to felicitate Professor Santi Sagarji for really formulating this award and thinking of how to make science making science going forward, and trying to rewarding all those scientists who are really doing wonderful research in their respective domains. For this, I request Professor Bharadwaj, Professor Palmaraju to kindly present. Now I request all the dignitaries to kindly take your seat. We now eagerly look forward to the memorial lecture. Now I request Professor Devendra Chakraborty, Chair of the Raghavarao Memorial Lecture, to introduce the speaker to the audience and those watching live in WebEx as well as YouTube platform. Professor Chakraborty.
Good afternoon, ladies and gentlemen. It's truly an honor to introduce today's speaker. Professor Devendra Ojha received his PhD degree from University of Strasbourg, France in 1994 in astronomy and astrophysics, and subsequently joined TIFR Mumbai in 1997 after postdoctoral positions at IUCAA Pune and IAP Paris, France. He is currently a senior professor in the Department of Astronomy and Astrophysics at TIFR. And as you all might have already known, he is the chairperson of TIFR Balloon Facility Committee. He was also chairperson of the Department of Astronomy and Astrophysics at TIFR during 2013 to 2019. At present, he is also holding the position of the Dean Finance of TIFR. Professor Ojha has contributed significantly across a number of research domains, including galactic structure, ISM, interstellar materials, star formation. And in addition, he is also actively involved in the design, development, and operation of astronomical instruments. His notable accomplishments in these areas include the discovery of the thick disk population in the Milky Way galaxy based on star count studies. This result now figures in the field's textbook. It's a kind of textbook material, and you can see its example in the a book by Galactic Astronomy by Binet and Merrifield in 1998, which was published. And he has also discovered a large number of young brown dwarfs in the galactic star-forming regions, providing new insights into the initial mass function. The discovery of infrared dark clouds in the Milky Way galaxy is another notable work that he has published. In addition, Professor Ojha has played a crucial role in the development and operation of many sensitive instruments widely used for scientific research. These include the operation of a 100-centimeter TIFR balloon-borne far-infrared telescope, the development of instruments for the ISRO small satellite mission to carry out the infrared spectroscopic imaging survey, which is in abbreviation called the IRSIS, and the development of a near-infrared spectrometer and imaging cameras for ground-based Indian telescopes. He contributed significantly to the near-infrared spectrometer, TANSPEC and TIR-CAM2, the abbreviations of which goes like that. The world-class near-infrared instruments developed by Professor Ojha and his team have had a transformative impact on astronomy through the top two telescopes in the country, the 2-meter Himalayan Chandra telescope and the 3.6-meter Devasthal optical telescope. He has published about 200 papers in various journals, and many of these have made significant impacts in the field. He is a fellow of the National Academy of Sciences, Allahabad, and the Indian Academy of Sciences, Bangalore. The group led by Professor Ojha received the Zubin Kembhavi Award for 2023 from the Astronomical Society of India in recognition of their efforts to promote observational and instrumentation work in astronomy and allied fields. Today, Professor Ojha is going to talk on, as you can see, the observational understanding of star formation in the Milky Way and infrared instrumentation. With this brief introduction, I welcome the speaker for this year's Ravipati Raghavarao Memorial Lecture in the Eminent Senior Scientist category, Professor Devendra Ojha from Tata Institute of Fundamental Research. Professor Ojha.
Good evening, and Thank you very much, Professor Chakravarti, for kind words. And let me at the outset thank the selection committee and PRL for awarding me this Memorial Lecture Award. And I also wish to thank family of Professor Raghavarao for instituting this award, Memorial Lecture, for his memory. So one of the criteria of the award when I was asked to fill in was that work should be aligned with the scientific domain pursued at PRL. And then I thought that today I should share with you one of the most important letter which I got from PRL almost 30 years back when the PRL offered me job offer. This is a letter I got from Professor Devendra. And unfortunately, I could not join PRL due to some reason, but my association with PRL was continued almost like fourth generation of astronomer here. I started with Professor Anand Rao, and I heard that Professor Anand Rao was actually the student of Professor Raghavarao today. And we started actually with Abhijit when he joined from IUCAA Pune. He came to TIFR as my postdoc. So I will say from first generation, then of course, second generation, third generation, now students of Lokesh and Manas actually are collaborating. So I really thank to all these my collaborators, students, postdoc, whatever I have achieved is because of their contribution. And also thanks to many other collaborators from other institutes, including my own collaborators from TIFR and so on. So actually, in fact, the first star formation paper on multi-wavelength aspect of one of the source in Milky Way was the first one, which Abhijit and I wrote actually. And then actually a lot of paper came on multi-wavelength studies of galactic star formation. Of course, TIFR that time was doing star formation using balloon-borne observations, but that was the beginning when we started all the ground-based data taken from various surveys and various telescopes. So really thanks to PRL, still we are continuing this collaboration. So today I am going to talk very simple fundamental problem. This is still debatable is how you form the low mass star like our sun. Of course, we know that there are many such stars, but still this problem is quite fundamental, quite debatable, and there are many other aspects of star formation. So what we know about the formation of sun-like stars is this theoretical paradigm where we know that at some stage where the cores which are formed in the large molecular cloud actually where when the gravity dominates the thermal pressure, they collapse, and then they go to these various phases of star formation, and finally they become as a star in the main sequence and surrounding planetary system. So, and I have actually put here some length scale, which will later on bother you. So I have written it here. So what is remarkable is that this kind of length scales at this collapse starts from like parsec scales, and it really reaches up to almost like 50 astronomical unit when you start seeing planets and stars. And of course, we know these early stages of this system. Of course, there is a good understanding how the sun-like stars are formed. But what we know observationally is the initial phases where you can observe the molecular cloud, you can study the molecular cloud, properties of the molecular cloud. And of course, you can study the stars. Now you can study a lot of exoplanetary system around the stars. But what is most important is these intermediate stages, which actually determines the future of the star, fate of the stars. Because most of the mass which like our sun has gained is at this stage, which are basically called inside and outside collapse phase, where a lot of matter is accreted and some of the matter is thrown away because of the conservation of the angular momentum. So this is the time scale roughly around 1 million years is very important. And this is the phase which is very difficult to observe directly. Of course, directly you can observe molecular cloud, you can observe stars, planetary system, but we don't have a special scale where you can resolve these intermediate stages, and which are actually the most important stages where actually most of the mass gained by the star, almost more than 10% mass is gained by the star at this stage, and which actually determines the future evolution of the star. So it is very important to understand these stages. So that's what today's talk, I am going to talk about, can we now handle these stages observationally? So I will talk about briefly about these early stages of low mass star like our sun, and what we know about these intermediate stages, which are very important stages. And I will try to prove you that these kind of studies actually can be done through the multi-wavelength studies, which are high cadence observational approach, and for which the smaller facilities are very important. In the era of the large facilities, which are like TMT or ELT, which will come in near future, still these smaller facilities like 1 to 4 meter class telescopes are very important. And during my talk, I will show you why this is important and why this long-term program are important. And that's why the sideways astronomy by these facilities are very important. And I will show you some example, which are very interesting results about these stages where sun-like stars can form. And if time permits, I will also talk about instrumentation which we develop and which we basically use to follow up these kind of observations. So let me come to the fundamental problem in low mass star formation in the very early stages, around 1 million time, 0.1 to 1 million time scale. One of the very important problem in the literature is called the luminosity problem. And this luminosity problem is basically is nothing but it is when you observe some young stars, which in astronomy term we call protostars. We have some theoretical concept how these stars are formed. So if we derive their theoretical luminosity from this accretion rate, we found that which is actually orders of magnitude less than what you observe currently for these protostars. So this basically a puzzling effect that if suppose you can imagine that when gas is collapsed and stars material is accreted through this disk into the stars through some rate which is called accretion rate. In that stage, suppose this is a steady rate, which we know there is rate right now like 10⁻⁻⁶ to 10⁻⁻⁷ solar mass per year, then it will take long time to form like sun-like of stars. So you cannot form these stars in a million time scales. So naturally, there is something happening in between which actually produce or make these stars in intermediate stages, and which actually nothing but not the study, it's called an episodic accretion, which happens and which we observe as we call them outbursts. So that actually solves this luminosity problem. And this problem is very important to understand the stellar evolution of these kind of sources. So just to now couple this accretion to this nice picture, which is basically the Hubble Space Telescope picture of one of the young protostars, low mass star, which is hidden behind the dust. Even in this infrared image, we cannot see these stars. And what you see here is a very nice discontinuous knots of gas and dust, which are basically thrown by these stars. So this is basically nothing but the jets or outflows which are thrown by these stars. And why this is happening? Because when the matter is accreted from the cloud, envelope of the cloud, through this disk, later on I will come to that, these are called protoplanetary disks. And when this material is dumped onto the star like our sun, in that system there is an instability problem because you have to conserve the angular momentum of the whole system because the star is rotating, disk is rotating. So to remove this angular momentum, you have to throw out this material in terms of jets and outflows. So what you see is these kind of nice outflows from the young stars. So basically these are called accretion-driven outflows in low mass star formation. And if we know these system, accretion-driven outflows very well, you can actually constrain very well the stellar evolution theories of these stars. So these are very important, and these are the basic parameters which we have to understand very carefully. One is accretion, one is outflows. However, there is a hint of direct observations of these kind of events which are happening in the early phases of the low mass star like our sun in terms of the thermal history of the solar system, which is preserved in our solar system. For example, if you see this meteorite, which is called Allen meteorite, in this meteoroid, you see these kind of materials, which are called chondrules or calcium aluminum inclusion materials, which are basically produced in the protoplanetary disk when these kind of violent phenomena is happening where there's a episodic accretion happening, means lot of material is dumped on the star and throws away, which actually produce this recurrent heating on the surface of this material, meteoroid, at a temperature roughly around 2000 degree Kelvin. And basically these kind of material tells you that there is some kind of history of, let's say, in the early evolution of the protoplanetary disk. And if you do the radio dating of this material in this meteoroid, we find that the typical age of these material which are produced is roughly like 1 to 3 million years. So that proves that in the early history of the star formation, you need these violent phenomena in terms of episodic accretion, which means that you have to dump this material on the stars in terms of a high accretion rate in terms of outburst. So that's what very important. So the direct observation hint comes from these radio dating of these meteoroids. And this is a nice picture now from James Webb telescope. Earlier picture was from Hubble Space Telescope. Here again you can see there's a young stars which is hidden even in infrared wavelength, but it can actually throwing a lot of this discontinuous knot of gas and dust in terms of outflows and so on. So what we now know that these stages of the evolution, like 0.1 million to 1 million years period in the formation of the sun-like star, is very important. And now what we understand theoretically is that when the gravitational collapse is happening of the molecular cloud, material is transported through the envelope to the disk. Basically, disk is produced because of the conservation of angular momentum, and then this just truncate at certain radius because the protostar which has been produced is rotating very fast, has a very high magnetic field. So this magnetic field line basically truncate disk at this radius, which are called truncated radius or magnetospheric truncated radius. And then this material is channeled through these magnetic field lines because of the rotating stars and truncated radius. You have a twisted magnetic fields, which actually carries the material through these magnetic lines. And then the material is dumped on the stars and very high shock velocities. So when material is dumped here in a very high shock velocities, then you can actually see a lot of accretion shocks. And that is what you actually observe indirectly. So what you observe is in accretion shocks in UVs or X-rays, where you can see how the continuum observations are changing, as well as you can see a lot of spectroscopic lines, which are actually gives hints of these shock emitting regions. So what we observe is basically we observe these hot continuum and spectroscopic lines from observations. And then we see the variabilities in these lines because this system is now not static, because material is continuously flowing and then it is dumping material to the stars till the star gain mass. So during this process, you have many types of this episodic accretion and outbursts are happening. So the system is highly variable. So if you can observe these variabilities in these spectroscopic indicators like lines or continuum, then you can couple these variabilities to the magnetospheric accretion funnel, which is produced by the magnetic fields lines. And then you can extrapolate and couple to the protoplanetary disk. And that way you can actually observationally study this system, and which can tell you how these sun-like stars are forming. So what is important is that short wavelength observations or spectroscopic observations are very important to understand this inner dynamics of the protoplanetary disk. So now the picture which we know is that you have an accretion disk around the star, which are also called protoplanetary disk, where at later stages planetary formation happens. Then material is forming, you see outflow jets and various kind of phenomena in the system. So basically accretion outflow system in a young stellar object like our sun, which form in earlier evolution, essentially tells that how can you form sun-like star in a Milky Way. Now let me come to the actual real observational picture. So this is just the cartoon of what I talked about, that you have a protoplanetary disk around the young protostar, which is just forming, which has not reached to the main sequence, where there is no nuclear fusion. All the energy which is produced by these stars are basically by the gravitational contraction. Basically, gravitational potential energy by contraction is released as a heat, and they basically heat the surrounding material, where you can purely see the gas disk, and then you see the rocky disk here. And what we know right now observationally is that you can actually resolve these protoplanetary disk from, let's say, 10 AU to 100 AU length scale through ALMA, which is the Atacama submillimeter survey in submillimeter wavelength, as well as direct imaging from HST or bigger telescope like 8-meter class telescope. And in the near future, when this near IR interferometer or optical interferometer will work, probably we can resolve up to 1 AU part of the inner protoplanetary system. But unfortunately, where most of these dynamics are happening, a lot of early stages of the star formation, where star is gaining mass and so on, is at this length scale, very less than 1 AU, almost like 0.03 AU. And these regions actually cannot be resolved by observations, the direct observation. So that's why what you need are indirect observations from optical spectroscopy, near infrared spectroscopy, or in UV region, because a lot of hot material here, which has temperature is very high, can emit UV continuum, and a lot of this intense radiation can actually emit a lot of optical and infrared lines. So that's why it becomes very important that spectroscopy and photometric large cadence observations are very important to resolve these inner dynamics. So that's what is the topic of my presentation today. So now what we know, the current picture is that, so you have a protoplanetary disk here, and then there's a surrounding gas, which is a partially ionized gas, which basically carried by these magnetic field lines through this magneto-accretion funnel, and they dump the material on the stars. And since a star is rotating, I will show you some example. And then periodic dumping of the material actually creates the mass of the stars, and star gain mass from that. So basically what you have to observe is this inner dynamics in various multi-wavelength observations. Okay, so what exactly you see in observation? Just to show a very simple example. So when system is in a steady state, when there is no carryover of the material, when material is just in other terms, in astronomy terms, if I say when the magnetic pressure of these star is equal to the Ram pressure of this galactic protoplanetary disk, then you have a steady state kind of accretion, which is happening in a very low rate, where mass is taken at the rate of minus 10 to the power minus 7 or 10 to the power minus 8 solar mass per year. But when this some kind of instabilities is happening in the protoplanetary disk, because a lot of mass is dumped. So when mass is dumped, then you can have a gravitational stabilities or thermal stabilities in the protoplanetary disk. In that time, suddenly this accretion rate increases, and these magnetic field lines carries the large material in the rate of 10 to the power minus 4 to 10 to the power minus 5 solar mass per year. And at that time, then what you see when there is a steady state accretion, if you observe this, in terms of, this is the brightness, we call it flux, as a terms of wavelength, then you can see these kind of continuum emission. But when there is a high accretion rate, when material is dumped here, suddenly this continuum is increased, brightness is increased, and you can see such kind of variability in these stars. And when they become very bright, then you can discover these sources. Okay, so that's what we do observationally. Unfortunately, when these systems like sun-like stars are in a steady state, they are very faint, or in quiescent states, you cannot discover them. But as soon as they go in the outburst, then you can actually observe them. So that's why these discovery of these stars are basically only we know 4 or 5 dozen of such sources. So it's very important whenever these stars, they went into the outburst, you have to immediately follow up these observations with long-term photometric and spectroscopic observations. So these are few examples of such young protostars, which are very classical example like X Lupi or F Orionis. These are the classical example of the sun-like protostars. So this y-axis is the basically epoch of observations, and y-axis is the magnitude of brightness. So whenever these stars are actually discovered, which means that whenever they went to the outburst, suddenly you see their increase in the brightness, or in astronomy terms, we call it magnitude. When suddenly their magnitude is become brighter, you can actually discover these sources and then you can follow it up. So unfortunately, unlike many other such kind of stars or other object, when you go, they go in the outburst, whenever you sort this one source to another source, their light curve is not unique, not universal. So these are basically called light curve. When you plot this photometric magnitude as a function of time or epoch, these are called light curve in terms of astronomy term. But each time when you discover these sources, every time you see different morphological shape or different kinds of their increase rate or decrease rate and so on. Unlike novae and supernova, when they are discovered, you find every time they have an identical light curve depending on what kind of supernovae or novae you observe. So that's the very difficult part, and that's why you need to observe them for long term. That's why long-term cadence observations are very important. Now, observationally, we know these young stellar objects are in a different form. Basically, if you can observe them in this space, X and Y, where this is the amplitude or magnitude of the brightness as a function of their epoch or time when they go in the burst, you can see that they almost fill all the phase space here. And so you can see all kind of variabilities in these stars. So basically, we have to study all these kind of variables to understand how the sun-like stars have formed. So in my talk today, I will basically pick up the object which has gone to the very high intense rate of outburst. Almost their magnitude has increased by 5 magnitude, or in terms of brightness, more than 100 times. And they have a long period of decay time. I mean, they remain in the outburst for a long time and then slowly they decay. So we have actually observed these sources for our study. So this program, actually called now MFES program, basically monitoring of these sources. These are the typical name of these sources, classical name called FE Orionis or EX Orionis sources, and program name is MFES program. So we started almost this program 2.5 decades ago. And since then, we have actually used several hundreds of optical and infrared observations from our own Indian facilities, and now slowly using outside facilities for the sources. So this program actually started in 2004. That time, these kind of alerts were known only from astronomy telegram, which used to come by email. Now we see a lot of such kind of alert from various surveys. And 2004, we started from all telescope in India, SCT, Mount Abu, even we followed with GMRT. And this first paper came about this famous, one of these outburst sources of McNeil Nebula, when Professor Anand Rao was also one of the co-authors with those sources. Since then, of course, that time we didn't have many near-infrared observation facilities, except Mount Abu have NICMOS camera. But now, more recently, this program has been extended to the infrared observations, thanks to new telescope, which has come up, like 3.6 meter telescope in Devastal, Nainital, and 2 meter now has a full-fledged near-infrared spectrographs, which we developed in TIFR. And now we have a complete coverage of optical, infrared, photometry, and spectroscopy of these sources. So now in my talk today, I will just give you few examples, observational examples, that how we can actually observe this intense inner star, this dynamics of these sources. So I'm calling it as a 1 and 2. So 1, basically how you carries the material from these magnetic field lines. These are called magnetospheric accretion funnel to the stars. And 2 means when you dump the material on the stars, then how the star can gain mass there. So I will just try to real observational example, which now we are able to actually pinpoint or penetrate these things. So this is the first example. This is one of the source which was actually alerted by Gaia Space Telescope when it suddenly went into the outburst from its quiescent phase in 2020. And this has a mass of like solar. This is almost like a sun-like stars, but very far away distance, almost 3 kiloparsec. And this, of course, we followed with our own telescope in India. And this is a beautiful light curve, which is called photometric light curve, where y-axis is the magnitude in multi-wavelength observations, from the shorter wavelength like U band to the longer wavelength like I band, from various surveys as well as from our own telescope and instrument. And you can see this nicely. We have covered this quiescence phase when a star was in a steady state accretion phase, and suddenly when it went into outburst, and we captured that, and then now it's slowly decaying into the again in the quiescent phase. So this is very important, because if you have to understand the whole stellar evolution of sun-like stars, you have to monitor these quiescence outburst stages, because these time scales are very important to constrain your modeling, which are actually used in stellar evolution theory and so on. But more important is from photometric observation, the spectroscopic observation, which are very powerful observations. So this is very nice spectroscopic observations, all from optical wavelength till in the near infrared wavelength from our own facilities. It is almost like 2.5 octave of wavelength which has covered. And these are multi-epoch spectroscopic observations. And this tells you a lot of things about the you can get a lot of indicators of inner galactic dynamics from these. For example, this is one of the spectroscopy line called hydrogen recombination line around 6,000 angstrom, which is basically called H-alpha line, where you can see there's a very intense emission as well as there is an absorption which is blue shifted. And in astronomy, we call it P Cygni profile. Similarly, in other lines also you see like calcium to IR triplet lines. So what you see here is that this, when I told in the beginning, when material is dumped on the stars through the magnetic field line, it produces a very high shock regions. And that shock actually produces these emission lines. And same time, when a lot of material is dumped, so you have to conserve the angular momentum. So you have to throw out the material. So when the material is thrown out through stellar winds, you can actually see this P Cygni blue shifted profile, because this material is thrown away towards your direction through the stars. So you can see this accretion driven outflows itself in these lines. So all these lines are very important, which gives you a lot of important indicators of star formation in the system. But if you have a multi-wavelength observations or different epochs, then they tell you more about the dynamics. For example, you can see this particular line which I was talking about has been observed in multiple epochs, and you can see this evolution of these lines. For example, you have a high emission lines and very intense absorption in the blue shifted, but suddenly this absorption is disappeared. So it tells that when the star, this is a highly variable nature of the source in the early evolution of the history of when sun-like stars are formed. So once you capture these variabilities, you can actually talk about, you can actually constrain your object parameters much better. So there are many, these lines are very important. But what we receive interesting result in these studies is that when we observe this source from our own facilities, when we submitted a proposal to the larger facilities like 10-meter kind telescope, actually it really gave a strong justification for our proposal. So this spectroscopic observations now was made from 10-meter HET telescope with a very high resolution spectrograph. And what you see in this picture is a very remarkable result, which is, of course, what I talked about so far is the blue shifted absorption, which is associated with emission lines, and which you can understand with accretion driven outflows mechanism, which is very common in the sun-like star. But in this case, what you see that this calcium IR triplet emission line is here, and there is a red shifted absorption here. So this red shifted absorption cannot come from the stellar winds of outflows. So what does it mean is that some material which is going away from you, away from the observer line of sight, and this material is nothing but it is the infall material which is dumped on the stars. So this is the first time it is reported in these lines, calcium IR triplet lines, although these kind of red shifted absorption were earlier seen in other lines, but this line is very important. This calcium IR triplet line is roughly observed around 8,000 angstroms, comes directly from the magnetic field lines, magnetospheric funnel regions. And so based on the velocity which we measure from this line, roughly around 25 kilometers per second, now you can work out on your analytical equations. For example, if we know the mass of the star, we know the mass of the radius, and we know this truncated radius of the disk, which is truncated by the magnetic field lines, which are now more or less constant, then you can actually calculate the infall velocity of this material, which roughly comes around 300 kilometers per second. So the material is actually thrown away by this high velocity. That's why it makes a shock. And then if you extrapolate it to your line of sight from where you actually observing this absorption, what you can constrain is the angle, which we call the position angle. So in this star, when we are observationally studying these stars, we don't know at what line of sight you can, at what angle you are observing at position angle. So if you can constrain the position angle of these stars, then you know all the observational parameters will fit much better your stellar evolution models. So why we found that this 25 kilometer velocities and this infall velocity can constrain the position angle of these stars, and which is one of the most important parameter. But the most important result which came out is that magnetic fields are very important in the formation of early stages of formation of sun-like star, because in this case, what is happening is that material, basically a truncated disk, is carried by these magnetic field lines with these velocities and dumped on the stars. Okay, so this is a very new result. Now, of course, we know that it's dumped by the star, then how the star gain mass. So I will come to now this inner region. Again, I will show you our new observational result. This is one of the source which we study to basically understand this inner dynamics of the star, this system called XUP. This is one of the very important source in the literature, which is we sometimes call touchstone young stellar object, because this XUP actually has been observed now almost since 140 years. First, it was observed in 1819 when people have started seeing outbursts. Then since then, it has gone to the multiple outbursts in 1945, 1955, 2008, and suddenly in 2022, we have seen another outburst in the sense that there's a high accretion rate, which has been produced by the instabilities and so on. And basically, we try to study these outbursts in this source. And so this is a beautiful light curve from our own observations and from various surveys and from small telescopes. These are from 0.5 to 2 meter class telescopes. And what we found is a remarkable result from that is that, so this is the photometric light curve in terms of this is the days, number of days where we observed versus the brightness in various wavelength, multi-wavelength. So what you see is that if you just take a chunk of the light curve here and you just zoomed it, what you see the periodic light curve in this basically in photometric high cadence observations. And not only that, when star is at quiescence, low state, you see these periodic variations. Suddenly when star goes in a high accretion state or in outburst, still you see this periodic variation. So these periodic variations are coming because the material which is carried by the magnetic field lines are dumped on the stars, and which actually producing kind of a hot spot. So this is we call in literature in astronomy as a hot spot. It is a material, and this hot spot is why the name hot spot, because the temperature of this hot spot is the larger than the surrounding photosphere temperature of the star. That's why it produces an intense UV radiations and emission lines. So that's a beautiful result. Not only in photometry, we also had a spectroscopic observation, high resolution multi-epoch spectroscopic observations. We found this periodic nature of the radial velocities. And so this periodic nature of radial velocities is very important because it gives you the rotation period of the stars. So we actually determine the rotation period of the stars, as well as information. We infer that it is basically produced by the hot spot. So I will just show you how it is done. I don't know if I can. I think I cannot run the movie here. So basically when this hot spot material is dump on the star. So both star and these spots are rotating. So when this hot spot comes in front of you, you see the increase in the light curve. When it goes, you see the decrease in the light curve, which goes behind the star. So you see these periodic modulations. And if you observe them in multi-wavelength observation in different filters, you can actually see some kind of phase shift, which I will come to later on in my slide here. So this is a beautiful result. So now we know the rotation period of the stars, and we know the light curve properties. So one can just do in astronomy, commonly we call it a folded light curve. We fold the light curve, photometric light curve with the rotation period, and we can just fit some sinusoidal equations with that, with some phase angle. So you can actually determine the phase angle, which we call the azimuthal phase angle, or in terms of similar thing, you can call longitudinal phase angle. Basically, when a star is rotating, at what angle it is rotating, you can determine from this light curve if you fold it with the rotation period, which we know. So this lower panel is actually showing the photometric light curve of this source when source was in quiescent phase, and suddenly it went to the outburst in 2022. So when it was in quiescent phase, we found that this longitudinal or azimuthal phase angle was almost same. There hardly any change in the phase angle. As soon as the star went into the outburst, you suddenly see there's a large phase shift in the phase angle. Almost this phase angle changed by 100 degrees and so on. So why it is so? So when it was in a quiescent stage, when material was dumped, it created the hot spot here, and hot spot was symmetric. And till here, when phase angle didn't change, hot spot was remained symmetric. As soon as the star went into the outburst, suddenly that phase angle has changed, and it has changed its position in the azimuthal direction. And not only that, it became asymmetric, which I will explain you later on. So this is very important result in the sense that when material is dumped on the star, how the star is gaining mass, because in that case, you have to basically uniformly distribute the mass across the stars, and that actually gives you a direct picture in these observations that when there's outbursts are happening, they are actually changing the location of this hot spot. Not only that, they are becoming asymmetric, and they are actually filling the material on the surface of the stars. So this comes from a direct observations. And not only that, we had a fantastic spectroscopic observations from SALT, which is a 10-meter telescope observations, and we derived the radial velocities. And if you see the amplitude of these radial velocities here, also gives the same phase angle. So this proves that these are the real observational scenarios. And there is this slight shift here, which I don't have time to talk about, is that there is a latitudinal shift also in the hot spot. So this is the longitudinal or azimuthal, and this is the latitudinal. So you see some kind of hint, because these are the points which is observed when star was in quiescent phase, and these are the points when it went in the outburst. So you have both azimuthal and latitudinal shift of this hot spot, which basically filling the material on the surface of the stars. So of course, these are from observations. Now you have to confirm from your modeling or simulations. So we have also done these global 3D MSD simulations. And beauty of this simulation is that now you know your observational parameters quite well. So you don't have to assume on initial conditions. So you know your observational parameter, position angle, your amplitude of the light curve, your accretion rate, and so on. So if you fill in these MSD simulations, what you see in lower panel is that this is the time versus the accretion rate. So as this is epoch of observation when you are measuring the accretion rate. And this is the basically shows you the material kinetic energy of infalling gas material on the surface of the star you are observing here. So you see when this accretion rate is steady state, you see that hot spot position is here. And suddenly when accretion rate becomes very high of the age of 15 days, you can see here that this hot spot has changed the phase angle, which actually seen in the observation. So you can exactly measure 100-degree change in the phase shift of the hot spot in the system. So simulation also proves that there's a azimuthal as well latitudinal change of the hot spot. Not only that, it gives you a lot of constraint on the inner geometry of the magnetic field, because what we know through theoretical paradigm is that when the material is, when source goes in the outburst, is try to push this protoplanetary disk closer to the stars, and then material is transported through these magnetic field lines. And generally we assume that there is a dipolar magnetic field configuration which remains throughout as such through the life of the stars. But that's not the cause, because when this happening outburst, when this hotspot is changing location, you can also see this funnel which is taking material through magnetic field lines actually also changes its position when accretion rate becomes very high. So you can actually see also the departure of this accretion funnel from dipolar magnetic field configuration to the other configuration. And that's very important because that actually creates a uniform distribution of material on the surface of the stars. That's why you form the sun-like stars. So another very important result why we should do multi-wavelength observation from small telescope, etc. This is an example where we have observed this source in U band, B band, and I band, all these optical infrared UV bands. And what you see here is that again the phase angle of the hot spot, which is called longitudinal phase angle, as a x-axis is the time of observations or epoch. So you see these cyan colors are basically from U band observations, and these red colors are from the I band observations. So you see that there is a kind of a shift in the phase angle. All are not showing the same distribution of the phase angle. So this is very important result, because when star was in quiescent steady state accretion, when there is no outburst, you see that all these light curve in different bands and basically are symmetric. There is no phase shift in the light curve. But as soon as, and which means that hot spot was spheric, but as soon as you go in the outburst, you see that there is a systematic phase shift from U band to the I band. And that's what you measure, this kind of a lag, a cometry feature here, which means that U band is ahead from the other longer wavelength, which means that the hot spot head is much hotter than the tail, which is the cooler tail, which is seen in the shorter wavelength. So multi-wavelength observation also basically gives you the, basically what physics comes out from that is that you can actually study the thermal structure of this hot spot also. So it's not that hot spot is a symmetric always, becomes asymmetric, fills the star surface, and which comes from these kind of very simple observations. So now what is the picture we know is that this is the picture when a star is in a steady state. You see this dipolar magnetic field where material is transported and dumped to the stars. You see these kind of symmetric hot spot on the surface of the star. And suddenly when it went to the outburst, because of various kind of stabilities, it not only changes the hot spot position, which become asymmetric, but also it changes the morphology of this accretion funnel, which are basically driven by magnetic field lines, and that basically fills up the stars here. So how much time have? Okay, I will try to wrap up. Okay, so now, of course, you can form these sun-like stars, but we know that generally stars are not forming in isolations. They are forming binaries and so on. So in these early stages now, actually, we have found out the inference or discoveries of these binary stars in this observation, again, by the simple observation from a small telescope in shorter wavelength and so on. So this is an example of Gaia 24CCY. This is another alert from Gaia when this one young star went into the outburst in 2024. Before that, there is another outburst in 2019. And very important here is that these two outbursts, when you compare 2014 and 19, remarkably has a similar morphological structure. So these red lines, red points are from 2024 outbursts and blue are 2019. And if you just fit in for at least for 150 days, these are remarkable similarities in their light curve, which is very, very uncommon, because you cannot assume in the stellar sources that always you will have the same light curve. And this kind of light curves can produce only when you have a binary star associated with. There is no other way you can prove that the similarities of and this intermediate variation in these type of sources can be seen. So basically what we have seen, similar profile, multiple outbursts, and one extinguished wipe kept on, but at least for 150 days, remarkable this. And this really told us that this is because of the binary nature of the source, because there are multiple sources. So that's what we actually found out when we searched the data in the literature, that this source was observed in long time back, 2013, by Keck telescope, which is a big telescope in adaptive optics. And they found actually two sources within the 0.5 arcsecond resolution. And then they didn't, of course, this paper was published, but they could not went further to this source. What we did is we actually used the Kepler light curve, Kepler K2 recent data, and found out the light curve of these sources. And we did some power spectrum analysis, which we commonly do in astronomy. And we found two periods, 1.14 and 1.78 days, which basically gives the period of these rotation period of these sources. But we don't know which source went into the outburst and produced this episodic accretion, because it's very difficult to find out. But what is important is that both the source turned out to be young stellar sources. And of course, we have to prove that. So naturally, one source went into the outburst, because when we studied the different light curve of this source, we found that one of the period around 1.178 days actually appeared just before the outburst. So each time if you see these panel, like this panel or this panel, it just appears before the outburst, which means that one of the source went in the outburst. And what about the second source? And in second source, when we actually fitted the light curve with this rotation period of the source, we found that it has a lot of these dippers in the light curve. So these are the light curve fitted by 1.14 days of period. And if you fit a smooth continuum, you find these dippers here. And these dippers actually can be produced by some kind of a galactic warps, which are seen in the galactic plane or in young star, which are very common. So if you have a disk, then when material is transported through a disk, you see a lot of instabilities or warps, which can actually produce these kind of dippers. So we finally found out that actually these scenario can actually produce the binary stars, which are both the young stellar object at different inclination angle. And this is actually the first time observationally we could actually get the inferences of these binary stars from this. So now in next 5 minutes or so, I will just talk about, of course, this all is about how do you produce sun-like stars, but then question is that how do you produce other stars which are more massive, like more massive than sun, which are like, if they are more massive than 8 times the sun, then can you form by this mechanism? And it turned out that, of course, there are a lot of theories which are known that how you form these massive stars, and particularly in PRL, there's a strong group which is working on this massive star formation. But it turned out that this accretion outflows mechanism, of course, works on massive star, which has not been possible earlier because of these kind of observations are not available there. But more recently, it has been found that, first of all, of course, in massive star, the problem is that these stars are quite far away. There is a complex environment around these stars. They are deeply embedded in their raw material or molecular cloud. So one is the thing is that if you can discover the accretion disk around this star, because you need a disk to carry the material onto the stars. So this is one nice example. This is the first time they did a VLBA, all these interferometer, radio interferometer studies, and they found these kind of spiral structure around these massive stars, which is of the order of like 1000 AU. And these spiral structure actually are known in the protoplanetary disk of massive stars. And then they follow up with these radio observations and found a lot of these spots, which we call major spots in these stars. And then they did a position velocity analysis of these measures. And when they fitted by the Keplerian rotation of the disk, they found that there is a Keplerian disk around these massive stars. And that proved that accretion disk can be seen in these massive stars. And then, of course, if there is a accretion disk around this star, can you basically prove that this is the same accretion outflow mechanism is happening in these massive star? For example, this is an example of massive star of 20 solar masses, where actually in the simple near infrared observations, when the source went into the outburst, one can actually, when they observed it in the near infrared wavelength like K band, they found that these lines, which are the indirect tracers of accretion rate, has increased by 4 to 5 order of magnitude in these stars, and which means that if you convert into magnitude accretion rate, you find that these kind of accretion rates are needed to produce these massive stars. So it is slowly turning out that one can actually prove this accretion outflow mechanism for formation of massive stars in this kind of source. But however, like in low mass kind of stars, you know that they have gone in the outburst based on optical or near infrared observations, which unfortunately is not possible with these massive stars. So what you do is you observe some kind of a emission called major emission in astronomy, like laser in optical light. One actually use it in a microwave wavelength region. And these major emissions in massive stars are produced by some kind of pumping. Basically, if there is a lot of shock happens on the surface of the star, that can actually pump out the photons, and you see these high photons in excited level compared to the ground state level, and just one passing photon can stimulate these emission and produce the amplification. So that is very common in the massive star region. So now there are many surveys of these major spots around the massive stars. So if you can see these flares in major emission, you can actually immediately follow them in the shorter wavelength, which is what was done by these group of people, and they basically found out that the accretion rate is very high. So we have just started these observation now. We are actually following these major emissions, and actually in one of the source, we have seen the change in major emission, which now we have followed with our Indian telescopes. And maybe in a couple of years, we may have some proof that accretion-driven outflows are very important in massive stars. So now actually we have expanded this MFES program, which I talked about worldwide, of using various small telescopes, including telescope in Thailand. I think Dr. Ramkesh is here, and we have heavily used this TRT telescope, now many telescope in Chile, Taiwan, and so on, so that we have a complete 24-hour coverage. When we are discovering these sources, we can continuously follow up. And I think recently we have published one paper out of that. So very quickly now, I just talk about, of course, all these observations and others are possible if you can actually develop your own instrument, because that can give you edge for your observations. So in TIFR, we have been doing a lot of space observation using balloons, ground-based telescopes, and so on. So we actually started our ground-based program almost in late '99 when Abhijit actually joined TIFR. And that time we actually developed this TIRCAM, which was a very small array, 58 by 60 to indium antimonide array, and heavily used in 1.2 meter telescope to characterize and calibrate this instrument. And since then, early 2000, now we have reached to this stage where we have a very state-of-art spectrometer. We are on the India's largest ground-based telescope, 3.6 meter telescope, and also at the time we also increased the spectral resolution of these instruments. So what I just wanted to emphasize that when we observed with Mount Abu in early 2000, so this is a 2002 paper which was published in Bulletin. Actually, we detected the L-band observations from Mount Abu. This is a beautiful image of Orion trapezium region, and it was actually observed in almost 4 micron from Mount Abu telescope that time. And that was really the exciting result. And it turned out that Mount Abu dry site is fantastic, even beyond 2 micron, you can observe it. And actually that encourages us to try this L-band observation from other observatories. And this is a nice picture. I just wanted to share that. That was an exciting result that time, because when you go longer wavelength, it's impossible to observe, difficult to observe, not impossible, because a lot of thermal background from telescope surrounding region and so on. So this is the thing which actually was quite notable. And now we have actually done a lot of this instrumentation for Indian telescope. And another thing which we are continuing is, of course, formation of low mass star and massive stars are important, but also important is that how once these stars are formed, like massive star, how they affect their surrounding regions, and you can actually study the morphology of the surrounding region and so on. For that, we do a lot of balloon-borne observations with our own telescope, which is a 100-centimeter telescope. And more recently, we have been doing far infrared spectroscopy at one of the important line in interstellar medium called C2 line, singly ionized carbon line, which actually falls at 158 micron in far infrared wavelength. And this line is very important because that can actually traces the material between the ionized region. If you have a massive stars, which can produce a lot of UV continuum, and that can produce this ionized region which is expanding, then you have a surrounding molecular region which is contracting. In between, you have this C2 layer, which generally we call photo-dissociated layers, which is contracting. So this layer can talk with ionized and molecular gas, and then you can actually study all the energy budget of the gas. And then you have a continuum observation. You can get the energy budget of dust. So you can actually study the morphology of or energy budget of gas and dust together. And this is an important line called fine structure line. And that's what we are observing. And this is a real picture where you see the C2 layer nicely embedded between this. And that is become very important. And it's very easy to observe C2 compared to the hydrogen, because the ionization potential of carbon is less than hydrogen. So if you have a massive star, it can easily dissociate carbon atom, carbon gas, and you can easily observe in far infrared wavelength. So for that, we have a unique spectrometer called Fabry-Perot spectrometer, where we use two Fabry-Perot. So one is actually tuned to 158 micron, and another actually are basically scanning around 158 micron. So at the same time, you can have observed spectroscopy line and 158 micron, and then the surrounding region give you the continuum emission. So both time you can actually study the gas and dust from the region which you are observing. And this is a very big experiment. This is a telescope which a total weight of this telescope is almost like 900 kg, and with all accessories it becomes almost 1200 kg. And we carry it with a balloon which is a volume of like 200,000 cubic meter balloon. It goes up to 32 kilometers, and then we observe for whole night, and then we observe various star forming region, and that's what we observe in C2 line. So this is an example, like these are our own observations. So these are the observation in dust continuum from Herschel, and these are the spectroscopic line, C2 line from balloon observations, and you see there is a nice correlation with this. So if you combine this, you get nice morphological picture, and this tells you how the massive star can affect the environment and so on. So this instrumentation program is a continuous activities in our group in TIFR. Many program now, these spectrometer from single slit to we are going multi-slit, and one of the spectrometer is in advanced stage. In few years, we will have a multi-slit spectrograph. Probably the first one in the country on 3.6 meter telescope. And now these instrumentation programs are very important for national large optical telescope, which may probably come in few years. And then also in space program, we have been continuing our interest in various programs. So just to summarize that, just to tell you that this is small class facilities, 1 to 2 meter class telescopes, long-term observations are very important. I think I justified that one with such kind of thing, you can actually penetrate the region which are not resolvable. You can actually study with these, and I think these will become very important in coming future, these small facilities. Thank you very much.
For such an insightful lecture on low mass star formation, as well as astronomical instrumentation being carried out at TIFR. And the observations are really helping to unveil the low mass and as well as the high mass star formations. We are really running out of time, but our students and audiences maybe wants to interact with you. So we may take a couple of questions. For that, I invite Professor Sasikiran Ganesh to handle the question and answers.
Okay. So thanks, Professor Ojha, and it's really nice to hear from you every time. I listen to your talks, I learn something new. So thanks for that. Well, the floor is now open for questions. Yeah. Chief.
Actually, I have a couple of questions. So one thing is like for FU Orion star, okay, you said the outburst happens because of some instabilities in the disk, and instabilities are basically short duration instabilities. It lasts for very short period, right? But in that case, the outburst happened and it reached the peak, and the intensity remains steady for 6,000 years, and still it is maintaining that.
No, so it's not happens all classes of objects. So for Epheorenis, that stabilities remains for quite a long durations. There another class of object, X loopy, where this is stability is in a short period of time scale. So this depends on what kind of stabilities you are looking on. So if there is a gravitational stabilities, which is a short-term thing because there's effect is very fast, but most of the time you see thermal stabilities in the system because once the material is piled up, then because of the properties of the disk, the viscosity of the disk and other, it remains for quite a long period. So all depends on what kind of stabilities you are talking.
It appears like steadily matter is being accreted onto the star and maintaining the luminosity at that same.
Yes, that can happen if you cannot drain out the whole disk.
Okay.
Because that depends on viscosity and other things. So.
Okay, so second question is, in one case you showed the outburst is exactly matching with the other previous outburst,
Yes.
periodicity. So because of that, you are claiming that that's a binary.
Not periodicity, the morphology.
Outburst duration.
Periodicities are.
Yeah, agree. So outburst duration matches with the previous outburst. And from that, you are telling that that is must be in a binary.
Yes.
But in our case, like in our X-ray binaries, even for the same system, we never see outbursts of exactly matching duration. Okay,
So
basically
only,
it depends on the mass accreted onto the object.
So not only the duration, but actually the morphology matches very. So even the intermediate fluctuation in the photometry is matching here. So that's what the strong claim of the binary nature. It cannot happen even with the planet around the star, because sometimes these gravitational stabilities can happen even when you are forming the planets, like Jupiter kind of planets around the protostally. But this binary nature comes, but because these intermediate fluctuations are also identical, not only the whole morphology.
The final one, this you showed this P Cygni profile for only H alpha, not any other emission line, that spectra.
No, I didn't have time, but it's seen in calcium IR triplet lines, in many other lines, of course. Yeah, which is very common.
Anyone else?
Thank you for a very nice talk, as well as briefing on what's all happening in this area of research. Since you have been heading this TFR balloon facility, can you just briefly tell our audience also that what facilities you have, what kind of experiments you can do, particularly for youngest faculty over here, who can make use of this facility for doing the experiments?
So TIFR balloon facility basically initiated initially to do, it started with cosmic rays, slowly it went to the X-rays, astronomy, then IR astronomy we are continuing. But parallelly, there are a lot of experiments were done on atmospheric sciences from PRL, of course, were pioneer that, then TIFR and so on. Now, actually, a lot of experiments, astronomy, of course, IR astronomy is one of the area, and particularly, I think at some point PRL we discussed with Mudit and other, UV astronomy is one of the aspects which probably we should do in future. But in atmospheric sciences now, people are doing a lot of experiment to climate, not climate science studies, but mitigation of climate kind of studies, which is a lot of, not even Indian government organization, but even the private organizations are coming with those kind of experiments in the science thing. Apart from that, science, there are many other experiments are done by, of course, these facilities is also used for student training. Many students from sometime from IST, Devendra, or sometime engineering colleges student, they come, they do the project. And it's really nice to see real observations, measuring pressure, temperature, various other things. So that also we do. And on the other end, now many young startups are actually coming to use these facilities for various kind of experiment. One of the experiment which young IITians which have opened the startup, they wanted to test their airship. So they basically airship and new drones. So first they tested with our balloons, their system and another thing. So as Professor Bhardwaj said, now this balloon experiment, you can think of any areas, not only astronomy, atmospheric science, or some other engineering aspect, but even biological sciences. People are actually testing their pharmaceuticals as well as other growth studies and so on. So we had some experiment from Hyderabad company in association with Singapore and other companies. So that is in brief actually. So it opens a lot of area, a lot of tests and so on. So balloon experiment depends. You can actually right now we can actually go up to stratosphere, which is roughly around up to 40 kilometer or 42 kilometer we can go. We had actually done some balloon fabrication, lot of R&D, where we have developed one balloon which can actually go to the mesosphere, just cross the boundary of 50 kilometer with very ultra thin polythene balloons. But then it can kg very small payload like 5 kg or 2 kg, but 10 kg kind of payload with very long duration. You can actually go from 20 kilometers to 40 kilometers height and so on. For example, like our telescope, which is like 1200 kg, we are carrying it up to 32 kilometer with 200,000 cubic meter balloon. But we have made a balloon which can actually carry 4-ton payload up to 10 kilometer also. So generally, most of the scientific experiments are done at the troposphere beyond 10 kilometer up to 18 kilometer, and then a stratosphere, because 10 kilometer is the area where planes are flying and so on. So these are the heights. So basically, height depends on what kind of payload mass you have, and then we can custom design the balloon here. So beauty of this balloon facility is that we custom design our own balloon depending on the specification of the user scientist.
So one just question on this. Do you also have some standard telemetry kind of support
Yes.
which you can
Yeah,
provide?
so
to
we
the
have
user?
a uplink and downlink. So we are using a 2 gigahertz. This is actually provided by ISRO
Okay.
long time back, S-Tech. And so it works, I mean, S-band. So we have one frequency designed for uplink to send commands, and there's a downlink for at the same nearby frequency we use it. So so right now our telemetry rate is actually our S-band is designed up to 500 bytes per second, but unfortunately we are not using it fully because our line of sight is not that perfect. But we have tested is about 200 kbps kind of rate. So in our infrared observation, we don't need much data rate. So we are directly getting the data online, but we can have onboard recordings and other things.
Okay.
So only thing is that we have a corridor of observations, which is 500 kilometer across, centered on balloon facility. We cannot cross that boundary because of various ATC permissions as well as RADAR are not safe. Yeah.
Yeah, I think I remember that there are some plans to go up to Andaman and cover.
We are discussing Andaman or Antarctica.
Okay.
Again, this has rediscussion has started.
Thanks. Okay, so any other questions? No. There's one.
Thanks for the nice talk. My question is even during the questions phase, the hotspot position remains stable for a long time. Okay, my question is that from the accretion disk to the magnetosphere, the magnetosphere is such a complex area in that region. So how is it remain the hotspot remain at a certain place for a long time?
No, so what happened in steady state cases, what happened that the magnetic pressure which is produced by this star and magnetic field lines actually almost equal to the ram pressure from the disk, and that time scale is larger. Okay, so when it goes to the outburst, you need some kind of kick in that case, and when suddenly you get some kind of a stability is try to push this disk towards the stars, and then it tries to twist the magnetic field lines. Okay, so that happens once in a while. Okay, but most of the time material is continuously falling, but rate is such a small that it remain in a steady phase, and that time that both the pressures are balanced, and that balance remains for a quite longer time space.
So after the outburst, will that come to the original place or?
Yeah, of course, I showed you the example that it comes to the original phase, but it takes time.
Okay.
It takes
Thank you.
Okay. So thanks, friends, and thanks, Professor Ojha, for.
Thank you very much.
So, ladies and gentlemen, we are approaching the closing of this memorable and enriching ceremony. So now I would like to invite Dr. Bhusit Vaishnav to provide a couple of vote of thanks and conclude the ceremony. Bhusit Vaishnav, please.
Thank you, Dr. Manas. So, good evening, everyone. It is my privilege to express sincere gratitude and appreciation at the second Professor Raghavarao, R. Raghavarao Memorial Lecture Ceremony. At the outset, we sincerely acknowledge the generosity of Professor Raghavarao's family for their donation, which has enabled the initiation of the Professor R. Raghavarao Memorial Lecture. We also extend our appreciation to Shanti Sagar sir for being here with us on this day, in spite of his demanding schedule. And also, as I understand, the family has joined us on YouTube. We extend our sincere gratitude to the PRL Council of Management for their thoughtful consideration and approval in establishing Professor R. Raghavarao Memorial Lecture. I express my sincere appreciation and gratitude to Director Professor Anil Bhardwaj and Dean Professor D. Pallam Raju for initiating the memorial lecture proceedings and enabling successful execution of today's event. I appreciate the prompt submission of nominations by all nominators following the announcement. I extend my sincere appreciation to all members of the Professor R. Raghavarao Memorial Lecture Committee for their dedicated efforts, including developing the guidelines, reviewing applications, and offering valuable evaluations in a very short notice and short time period. I extend my sincere gratitude to Professor Devendra Ojha for graciously accepting the invitation to deliver the second Professor R. Raghavarao Memorial Lecture and for his presence with us today. Professor Ojha, your distinguished expertise has significantly enhanced our understanding of observational research on star formation in the Milky Way and of advancements in infrared instrumentation. We extend our sincere appreciation to the purchase team for their prompt and effective work in securing the silver plaque, which all of us can see here. I would like to express my sincere appreciation to the volunteers from the Dean's Office, Registrar's Office, Director Office, CNIT, PRL Administration, CISF Canteen for their dedicated efforts in ensuring seamless operations. Thank you to everyone here and watching on YouTube for joining with us. Your contributions made this event valuable, and we hope you enjoyed it. Thank you for joining us once again. Enjoy your day, and we invite you for a cup of tea outside, and you can interact with Professor Ojha also. Thank you.